problem number 39, combination sum. So you are given an array of numbers called candidates and a target value called target. The goal is to find all combinations of numbers from candidates that add up to target. And importantly, that we should know that we can use the same number multiple times in a combination. We should return a list of all unique combinations that meet the sum. So if we have an example for that, let's look at this one. If we have 2, 3, 6, 7 as candidates and the target is 7, we can add 2 2s and 3 to get 7. We can add the number 7 to get 7 as well. And this is how it works. I guess it's a pretty easy problem to understand. And there is multiple ways to solve this problem. I would like to go with the backtracking solution because like to solve the problem, we use backtracking, and let's talk about how it works. So backtracking, the backtracking concepts is that backtracking is a method to explore all possibilities. In this case, we explore all combinations of numbers that sum to the target. If combination doesn't work, we backtrack or like go back and try another one. And I guess we will use a recursive approach. So we use a recursive function that tries all possible numbers in the candidates array, keep track of all keep track of the numbers used in the current combinations, and stops when the combination equal to target, which is a valid combination, and the combination exceeded the target. So the valid is invalid, like stop exploring further because if we exceeded it. So let's try to think about this step by step. So first we will have a result array, and this where we put all of our results, and we should return this array. I guess we need to create a function. We call it backtrack, and it will take 3 main variables. I guess like we take the remain, and we take a combination. Let's call it comp, and we take start. As we said before, the result array, this where we store the valid combinations that sum up to the target, and we have the backtrack function. This should be the heart or the main the heart of the solution, and it's a recursive function, so it's a function that calls itself, and we should track the remaining target. So we start with a full target and reduce it each time we add a number to the combination. After that, we need to track the current combination. So the combinations array holds the array, and we have which we have picked so far. In the end, we should track where we are in the candidates array. The start variables ensure that we don't reuse real candidates, only allowing us to reuse numbers from the current or later positions. So let's try to see how we do that. So first, we need to think of base case. So if we are working with a recursive function, we should make sure that if we recursive function is a function that calls itself over and over, and we want to make sure that to find a base case or a case that we tell our function to stop calling itself and stop executing. So we have if the remain equals to 0. If that was the case, that means we hit the target exactly. So we need to save the combination. So result the push, we put the combination, which is comp, or no, we need to put all. Let's 1, 2, 3, everything in the combination, and we should return nothing here. Okay, so we need to loop we need to loop through the candidates array and starting from the start. So we do like a loop here for let I equals start. I should be less than candidates dot length, and I is plus plus. Okay, I will say my const let's call it C, which will equals, let's call it item candidates of I. Okay. So we loop through the combination array. Oh yeah, something I did forgot here. If there's another base case that if the target, if the remain is less than 0, we should just return nothing here. So because if the remaining target goes below 0, we should stop exploring the path. This is one of the base cases that I forgot to add. So okay, let's go back to the loop. We should add the item to the current combination. Like I would say the comp dot push the item, and yeah, and let's say also we need to call the backtrack function here to explore more. So we need recursively we try the same candidate again, because we can reuse the same number. So we put the remain and minus the comp minus the item, sorry, and we add the comp, and we add I, which is our starting point, and we take comp dot pop our item, or the last one, which is like by track. We should backtrack by removing the last number added, so we can try the next one. And yeah, and I guess we need to go outside here and call the backtrack function, and we add the target as a remain, and we need to add an empty array, and we need to add 0. And let's submit and see if it works or not. Okay, it did work. Let's try to discuss again here the solution. So again, we did talk about the backtrack. So this is the heart of the solution. It's a recursive function that tracks the remaining targets. So we start with the full target and reduce it each time we add number of the combinations. We also tracks the current combinations, because so the combination array holds the numbers we have picked so far. And lastly, it tracks where we are in the candidates array. The start variable ensures that we don't reuse real candidates, only allowing us to ensure numbers from the current or later positions. So we need also to, if we're talking about the stopping conditions, so we have base case 1. So if the remain equals 0, it means the numbers in the combinations sum exactly to the target. So we have we save the combination in the result. We have a base case 2, so invalid combination. So if the remain is less than 0, it means the current combination exceeded the target. So we stop exploring this path further. Let's talk about the recursive exploration here. So the function loops through the candidates starting from the start, and for each number in candidates we do 3 things. We add we add it to the combination. Number two, we recursive to explore further using the current number again, because we can use it in the description. Three, the backtrack, we backtrack by removing the last number from the combination and trying the next candidate. Backtracking here is like after every recursive call, we backtrack by removing the last number added to the combination. This allows us to try new number combinations on the next iteration. So this is why we go through it. So we can go through an example for that. So let's say that the let's say that the candidates array equals to an array which has 2 and 3, okay, and the target equals 5, for example. So we should start with an empty combination and target equals to 5, okay, and we will try the first one, which is 2. By here trying to the combination will first, let's just put the combination, which is the comp array. The comp will equals yeah, the comp I guess will equals 2 because we starting to add the first one, and the combination and the remain, I guess the remain, let's just put the remain. The remain will equals 3. So the remain will equal 3 because 2 minus 3 equals 2 minus 5 equals 3. We need to try, we can add 2 again here. So the remain will equals 1 and the comp will equals 2. And we will try to add another 2 and the remain will equals minus 1. And this one is invalid backtrack, so we backtrack now. We're trying add 3. So how this will work? So first we remove the last one here, and we'll try with different one. So here the combination target, it will be 1 minus 3, which will be valid 1. So, and after that we try to continue until we found here. So the combination, it will be 2 3, for example, or like yeah, it will be 2 3 like this. It has nothing else, like just it can be 2 3. So if this one will work, yeah, it will work like that. After that, we can continue the process until the possible combinations are explored. The term complexity, it will be O of 2 in the power of n, where n is in the power of t, where t is the target and this is because we try all possible combinations of numbers from candidates array. So that's it for this solution, and see you in the future.